students. Today we will discuss power spectrum estimation. It has three methods to estimate the power spectrum of a signal. First is periodogram method, second is parametric method, third is non-parametric methods with further three methods in these. But before going to this topic, we should have some knowledge of random signal theory, which is prerequisite for this topic. And these are some of the topics in that random signal theory. So first we will look at in the random signal theory. And what is a random signal? We know very well that a random signal is a undeterministic or non-deterministic signal. That is, for example, air temperature, air pressure, which fluctuates randomly as a function of time. There are different temperature in different cities, depends upon location, depends upon weather. So it is randomly fluctuating with time. In electronics, you can have that thermal noise voltage generated in resistors of electronic device such as radio television transceivers. So there are basically lot of random signals are there. These signals are basically infinite duration because we can't limit in time, and infinite energy signals, okay, because of this randomness of nature. For example, air temperature in different cities. We are taking an example to discuss in detail. Let us taking as air temperature in different cities, city A, B, C, and we have the different temperature with respect to time plot. And these, suppose we have taken 3 cities, we can take n cities obviously. Set of all possible waveform is called ensemble. Ensemble means a set. Ensemble of time function because it varies with time. And further we can call it completely as a random process because it is a random process. One waveform for one city is called a sample function. There is n sample functions. Here 3 sample functions are there. And the complete set of these sample function is known as a random process, which is denoted by XTS or generally XT, where S is for set or sample space. That is for S1, S2, S3. Here on the 3 cases are there. And for the single waveform can be represented by small x, a dummy variable, TS, XTS or XT in short form. XT, it is representation, XT, SI and XIT. There are different kind of representation. Let us take a further exploring the example. Let n sample function, that is n series are here, n is some positive integer number. Now sample space becomes S1, S2, S3, Sn, that is for different cities, each city, and we can write it as I, where I equal to 1 to n. Now further plotting the sample functions for each city, we have plotted the function, and we can write it as XTS1, XTS2, XTSN. When we call it X capital, then we are talking about the random process. When we are taking it X small, then we are talking about the dummy variable which can root any position in that random process. Now random process XTS or XT in easy form. Let's find out this value of this random process. Value of this random process at any certain instant of time, that is Tk. So at that Tk time, we must have n observations. Observation 1, that is x1 Tk, observation 2, x2 Tk, observation 3, xn, x3 Tk and xn Tk. So we can calculate all the observations, that is in terms of random process, that is x Tk S1, the first random process at time Tk, it becomes obviously this one. Second random process xt S2 at time Tk, it becomes this one, and so on. So this is the set of observations, n observation at time instant Tk, which becomes random variable. So there is a difference between random variable, that outcome of any experiment, here an experiment is air temperature of different cities. Outcome of any random experiment can be mapped into waveform as a function of time, then it is known as random process as a whole. And if it is mapped into number, then it is a random variable. We have mapped only for the one time instant. Further we can map for different time instant, and we have a set of random variables. Okay. Now, what is probability density function? We have heard it many times, of continuous random variable. So, probability density function, in easy words, we can assume that it is any function, any mathematical function, which can specify the probability of that random variable falling within a particular range of values. Okay, it may be any function which can specify the probability of that random variable. And why it is in particular range? Because in continuous time domain, we cannot access exact instantaneous time. For example, I'm saying that this is the time 9:30, but while I'm saying it is 9:30, it is obviously 9:30 plus some nanoseconds. So exactly in the practical scenario, we can't have the exact time duration or exact measurement. Suppose I can tell you that it is 1 mm, but it is not 1 mm. It may be 1 mm plus something or 1 mm plus minus something, but it is not exact 1 mm anytime. So, for example, 5 seconds mean 5 point infinite zeros, so it cannot be calculated actually. So exact time, exact measurement is not possible. So we can say that, okay, that's why we use the particle range of interval. That is why we need a time interval to identify the probability, not the exact time. For example, let number of bacteria dies in body with average lifespan 4 to 6 hours. Here it is a random process, number of bacteria dying, and probability of one bacterium lives exactly 5 hours, because it is exactly, so we don't have that capacity to find that exactly what, so it is 0. So probability bacterium dies between 5 hours to 5.0 hours. So we have some time interval now we can calculate probability, and let us say it is 2%. Now probability, if we squeeze the time interval by 5 hours to 5.001 hours, then probability becomes that, let us say, obviously probability will decrease because the time duration decrease. So it is the same ratio, it is 0.2% suppose. Keeping constant probability of dying bacteria during time interval upon duration of time interval. That is, in first case 0.02 upon difference between this one 0.01. In second case it is 0.002 and difference is 0.001. So keeping this constant, and this constant is 2 by r, obviously, because it is in hours and it is probability. So this particular function, for in this case, for exactly for 5 hours, this function may be defined as a probability density function. It is called the probability density function for dying bacteria at around 5 hours. Okay, it may be called as, because it can calculate probability of random variable at any instant of time, because it is that function which can be used. It can be used to calculate probability in different time window. For example, probability bacteria lives longer than 5 hours but shorter than 5 hours plus 1 nanosecond. It means a time interval of 1 nanosecond. So this is the PDF, probability density function, 2r inverse into 1 nanosecond time interval, and it is the probability of value 6 into 10 raised to minus 13. You can convert 1 nanosecond into hours. Okay. Now a further class of random process is known as stationary random process. Suppose words as they say stationary, so it means will become stationary at some time. So a process, we have plotted the same process, and we are observed in the time interval t1 to tk. Okay, in this time interval we have observed the random process. We have set of some random variables. At time t1 we have set of random variables. At time t2 we have set of random variables. At time tk we have set of random variables. So this particular range we have random variables. T1, it is suppose xt1 is the random variable, t2 xt2 is the random variable, tk xtk is the random variable. Okay, we have saved these random variables. Now in second case we move to time shift of t1 plus tau. That is, in t1 plus after tau time shift, now again we will do the same process. That is t1 plus tau to tk plus tau with the same interval, and again finding the t1 plus tau, finding the random variable for this case, finding the random variable for this case. So now we have two set of random variables. First for t1 to tk, second is t1 plus tau to tk plus tau with the same interval. For example, tk is 1, 2, 3, 4, 5 and tk plus tau is 1.1, 2.1, 3.1, 4.1, 5.1. Tau is 0.1. Okay, so in these two time intervals we have calculated random variable for this random process. Now, if joint PDF of two sets of random variable are identical, this is the joint PDF, PDF1, PDF2. It is combined random variable set, and this is random variable set second. If joint PDF, joint probability density function of two sets of random variables are identical, then random process is called stationary. It means for any time interval set, for any delay tau time shift, all the time the joint PDF is same or identical, then it is stationary random process. But obviously in practical nature it doesn't hold true always. So a random process is divided into number of time intervals. The various sections of process exhibit essentially the same statistical property. Then that process is random, stationary random process. Statistical property here we can call it as joint PDF. Further, there are other statistical property also. If it is true, if joint PDF are same for all time shifts and for all k and for all time duration, then it is said to be strict sense stationary random process, which is very rare to find, but it is in theory, obviously. Now, mean or average. Second statistical property is mean or average. Statistical, it is also known as statistical average. It is also known as ensemble average. It is the expected value of random variable or expectation of random variable. We call it like that. E. E stands for expected value. And it is the symbol of mu xt or e raised to e of the function random process e of xt. And it is also written as this form x fx dx, and this xt is shown that it is the function, it is the PDF of random process xt, that is fx xt PDF of random process xt first order. For strict sense stationary process, PDF is independent of time. That is what independent of time means. In any time window we find that same properties. In the last case we have seen that in any time window we have got the same properties, so it is independent of time. So mu xt or mean or average is always a constant value for all value of t, because now it is not varying with time. Autocorrelation, second statistical property is autocorrelation function of random process. Now let two random variables are there, xt1, xt2, or we can also write it xt1, xt2 like this. In some books it is written like this, in some books it is written like this. So we must know all the notations at time t1, at time t2. Now it is a symbol of random process. It is like a gamma function, gamma, or that is autocorrelation of the same random process at two different time instants, x, that is for the same function at two different time instants t1 and t2. It is a representation which will be used further many times. And further we can write it in other form, rx t1t, when in general we use this r when we are talking about it is in time average form. When we are talking about this form, it is in statistical form. We will further explore these forms. Now it is the major form. We will use this form actually, and it is what expectation of random variable and random variable 2, both the random processes at time t1 at time t2, or the two random variables. And again using the same formula, 2 integration, now it is double expectation, so then in 2 integrals, 2 dummy variables, and 2 joint PDF. It is a joint PDF, single PDF having 2 random variables, second order PDF for joint PDF, and dx1, dx2. So it is these are different notations of the same function. Sometimes it is written as xt1, x1, sometimes xt1, fxt1. It is all the notations written in different books, so don't get confused. Now let the time difference, role of time difference t2 minus t1 equal to tau. We have taken the time difference of the same random process having 2 random variables at different time instants, and it is t1 t2 minus t1 is equal to tau, that is time difference. So the same expression same expression can be written as gamma x t2 minus t1, that is minus tau, or t1 minus t2, and it is first random process at time t1 minus tau. Suppose this is t1, one instant is t1 minus tau, second instance is t1, first case, or first t1 and second instance is t1 minus tau. It means either these two value or these two value. In this case we are taking these two values, in this second case we are taking these two values. So when we are moving forward, then it is a positive tau. When we are moving backward, then it is negative tau. And it is found that autocorrelation function is even function. When we are moving negative tau or positive tau, it behaves same. So it is for a stationary random process. For a stationary real valued random process, autocorrelation function is a even function. Behave evenly from the from any point. Okay, and this is the expression of this generalized expression. We have taken that gamma xx tau is equal to e x t1 plus tau into x t1. That is, first is t1 plus tau, second is t1, or vice versa. We can take it. For a strict sense stationary random process, we have seen earlier, joint PDF depends on difference between the observation time interval t1 and t2. Suppose in the strict sense stationary simple, we know that joint PDF only depends upon the time interval. It should not depend, but it may depend upon the time interval. Then it always depends upon the time interval tau. Okay. Now obviously we know that strict sense stationary random processes are difficult to find. So we have found another class of random process, which are the non-stationary process. Other than strict sense stationary process, all other processes are non-stationary process. Non-stationary process with the property that mean value of the process is constant. Mean value of process is constant and it is the same as in strict sense stationary, but it autocorrelation depends only on the time difference. It is extra term we have added. Mean value is process is constant, and that is a strict sense stationary process in which mean value is constant for all time. Joint PDF is same as for all time. Now here we have added extra term that mean values process is constant and autocorrelation depends only on the time difference tau. Then it is called a wide sense stationary. We have loosened the restrictions. Okay, and the first case is mu x is equal to mu x for all t, and then autocorrelation function at two time difference t1 and t2 should always depend upon the time gap tau. If time gap varies, then the function will again same for all t1 and t2. For example, suppose we are taking the t1 and t1 plus tau, finding the autocorrelation function here. Suppose here is a random process. We are calculating random autocorrelation for the random process at t1 and t1 plus tau this time interval and calculate it. Again we are interested in t5 and t5 plus 2 tau time duration. That time difference tau is same but time is different. Okay, and we have calculated this one, and other time instant t7 and t7 plus tau we have calculated. So we have calculated in these different time instants, but the time difference is same of the time interval. Then these all autocorrelation functions will remain same. This is the condition. For example, we are in numeric form 1 to 1.2 we have calculated 3 to 3.2, the tau is 0.2, gap is 0.2, 7 and 7.2, or further we can take as 1.2 and 1.4 also. The literal shift, very small shift or very large shift of the window, but the autocorrelation function will remain same. Then this is known as wide sense stationary process. Now what are the properties of autocorrelation function? First property, it's a tau equal to 0. When we will put tau equal to 0, obviously, then the expression becomes gamma xx tau here 0, and we have the expression that from the last expression we have the expression tau equal to 0, then it is xt1, it is also xt1, it is the same case. So it is x square t1. That is what? It is the mean, it is a square, mean is average, mean square value of the process, random process. So we can get mean square value of the random process while putting tau equal to 0. And second, we also know that it is even function. It is evenly behaving in the positive side as well as the negative side from the origin. Gamma xx tau is equal to gamma xx minus tau. It is a positive time shift, it is negative time shift. And third is maximum value at tau equal to 0. Maximum value of tau, that is maximum value of autocorrelation function, is always maximum at tau equal to 0, where there is no time shift. It is mean when function is related with itself. Okay, then obviously it is a maximum similarity, and then we have the maximum value. When we are making the time difference, we will lose the similarity index and we have less similarities. That's correlation in exactly what is. Now it is what is the physical significance of autocorrelation function? It provides a means of describing the interdependence of two random variables, that is obtained by observing the same random process xt at time tau seconds apart. Two random variables xt1 and xt1 plus tau. That is what how the random variables are depending on each other. Further, we can characterize by this function a random process in terms of rapid random process or slow random process. That is, more rapidly a random process changes with time, then we can identify by more rapidly autocorrelation decrease. Autocorrelation decrease very rapidly, so it is a random rapid process. And it is when it is autocorrelation function is slowly decrease, and it is a slow random process. Further, we have some definition of decorrelation time. So it is given that if time taken for magnitude of this autocorrelation function to decrease from maximum to 1%, to maximum to 1%, it is for this case now. Okay, 1% of its maximum value. We can scale at any level actually. We can put it here. It is 1% of here. I think around it will be 1%, or if it is 90%, then it is here. So we can modify our definition as per need, but it is the decorrelation time. We can move this value to at any value. Okay, if it is 90%, then it is just here, and it is 1%. It is maximum to 1%. It is here, decorrelation time. So it is the significance of autocorrelation function. Now in the next part, we will discuss the power density spectrum and energy density spectrum of the random process. Thank you very much.